why should we even care about transmitting classical information using quantum systems? Because we know that classical systems work very well. Apart from the obvious security advantage like you get from QKD, there is a point where you transmit your signals over very long distances in free space or in optical fibers. And if you're not able to use repeaters, these signals will be attenuated. And for example, if you use two coherent states of opposite amplitudes, these will be so attenuated that their uncertainty regions will overlap at the end. So the transmission rate will be fundamentally limited by the distinguishability of the signals. So the model for communication of a classical information is this one. I'm going to recap it very briefly. You have a classical variable x that you want to transmit. You encode it into a quantum system, which is transferred on a quantum channel, which changes the system, and then you have to perform a decoding operation to estimate the initial variable. In particular, we're interested in using bosonic systems, in particular light or the electromagnetic field. So I'm going to talk about modes. Each mode is represented by its creation and annihilation operators. And a very important class of states is that of Gaussian states. These have a thermal distribution in the photon number, and then I can do some operations on them, some unitary operations. So if I start from a vacuum state in phase space, I can displace it, I can squeeze it, which changes the uncertainty in the two quadratures, and then I can also perform some linear optical operations, which will basically rotate my state in phase space. And if I have multiple modes, M-modes, this will be a general rotation in the larger phase space, which can be realized, as you probably know, by linear optical interferometry. That's what I'm gonna call U in the rest of the talk. The quantity we're interested in is the maximum information transmission rate that can be attained by sending an alphabet of signals rho x with probabilities qx through the channel phi. This is given by the Olevo quantity, S here is phenomena entropy. And in particular, the maximum you can attain over all alphabets gives you the channel capacity for product encodings. For Gaussian channels, which represent very simple transmission that you can imagine like loss or thermal noise, this capacity was computed and actually shown not so many years ago that it's achievable by using very simple signals at the input, so coherent states. You just shine your laser and basically you will be able to communicate at the maximum rate. The measurement, which I'm not going to talk about, is of course going to be much more difficult, but let's focus on the channel which is non-Gaussian, and it's a phase noise channel. So this arises from physically motivated situations where you have, for example, a variation of the optical path length, which actually takes place during transmission on the channel, for example, due to thermal fluctuations, nonlinear Kerr effect, or atmospheric effects. So what I'm saying is that when you send a signal, it experiences a certain phase shift, and if you send the signal after that, it will experience a different phase shift due to a variation of the optical path length. This is an example of measurements of the optical path length during time of day. You can also have extrinsic causes due to your setup. For example, if you have a photodetector and you're measuring your signals, the effective field that you see will be dephased, because we know very well that the detector counts photons but cannot measure the phase, let's say, in this setting. Or in QKD settings, you might have an eavesdropper which is trying to affect the key distillation procedure that Alice and Bob operate. For example, this is very relevant in coherent state QKD. So the idea here is to take correlations. So imagine that your noise variations have a time scale, a typical time scale big T. If you're able to send signals short enough, big T, you can send M of them, where M is roughly equal to big T over small t. So the channel I'm going to consider actually takes n inputs of n subsequent signals, and these signals will experience the same phase shift. After the mth signal is passed through, the phase is completely randomized, okay? Now, very quick facts. If you send photons, if you are able to produce photons of arbitrary photon number, you can attain the capacity of a channel. But these, of course, are challenging experimentally speaking. Whereas coherent states are highly affected by this phase randomization. So the channel is described in this way. As you can see, it's acting with a phase shift generated by the total photon number on the M modes, and then randomized. So this effectively decomposes the input state into a direct sum in different blocks with fixed total photon number. Now, again, if you're able to communicate with Fock states, this will not be touched by the channel, and you win. But you are interested in studying what happens to signals which are less difficult to produce in practice, for example, Gaussian signals. Now, for a generic alphabet, the first thing we show is that you can always increase the rate by doing a randomization with a linear optical interferometer. What I'm saying is that if I have a state here, or family of states, and I apply before the channel a random linear optical interferometer, this will increase the rate. This can be proven by concavity of the entropy, essentially. And then the next thing we have to look at is how to compute this average. So the average state with respect to this randomization. This can be done, and essentially the only information that is left of the input state after this randomization, which is helpful, is in the diagonal, in the probability distribution of the total photon number. And the blocks, each block with fixed total photon number is completely depolarized. If you plug this expression into the expression for the optimal rate, you get an entirely classical expression. You see, you have some entropies and then a combinatorial factor, and everything depends on the photon number distribution of your input states. You can write it as this also. Now, let's go to Gaussian states. First things first, you can reduce to pure state ensembles because of convexity. And then you can also get rid of the linear optics part because we are already using it in the randomization. So what I'm saying is that the best Gaussian alphabet to communicate on this channel, the best strategy is to produce single mode squeeze coherent states and then randomize with our linear optics. In particular, if you produce only coherent states, we know that the photon number distribution is a Poissonian in the total energy, and so you can actually further reduce to sending just a modulated, a coherent state on the first mode modulated in energy, and randomize the energy with your linear optics. And you get this expression, which is again a classical expression, which you just need to optimize over the energy distribution. Now this contains a part which is the infamous Poisson channel, for which the classical capacity is not known still, and a combinatorial factor which tells you about the advantage you get by sending these M signals correlated. From now on, we have to rely on numerics because this optimization is hard to carry out analytically. And basically, we have an upper bound, which is based on finding the best modulation of this coherent state here. And then we have two lower bounds, which are based on an on-off strategy. This on-off strategy basically is to send either a vacuum signal or a very bright coherent signal on one input, and then always the randomization. Similarly, we substitute the coherent state in this on-off modulation with a squeeze coherent state, and the results are shown in the next slide. Now I'm plotting the rate as a function of the energy per unit of capacity. And you can see that these dot dash lines represent the coherent state rate. And here you have the upper bound for several values of M. Now, this is admittedly very little, but there is an advantage that you can see. I'm saying that a very specific and simple squeeze coherent strategy is surpassing a loose upper bound on any coherent strategy. Of course, this is not much. We wanted to go a bit beyond this. So what we considered is to compare essentially strategies with 2 or more pulses, which allow us to change and to choose which kind of pulses you're using. You can use coherent pulses, you can use squeeze coherent pulses, or you can use Fock states. The results are shown here. Essentially, I would like to point out 3 things about this. The first thing is that if you move from a binary to a ternary encoding with squeeze coherent states, you can push up this little advantage that you saw and show a visible advantage. And you expect that if you start increasing again and again the number of signals in your modulation, this will give further advantage. Of course, I'm comparing with a ternary coherent encoding, which is this one. Then the second thing I would like to point out is, of course, if you use Fock states, since they're not touched by the channel, you're going to do better than anything else. However, you might say that in some cases it's better to produce 2 squeeze coherent states rather than 1 Fock state, and in that case you can beat Fock state communication. Moreover, if you add losses now on top of your phase noise, you send your signals over very long distances, and these get attenuated. Already for small attenuations, you see essentially that squeeze coherent states can beat even Fock states, so they're more robust to losses with respect to Fock states, and they're also more robust to phase noise with respect to coherent states. Finally, we're working on also extending these results to private capacities, so essentially secure communication. You can see very early results where we already seen an advantage with respect to coherent states. And you might be wondering what happens in real life is that if you know that your communication procedure is going to be affected by phase noise, essentially what you want to do is to use a bit of your signals to exchange a phase reference. So you try to estimate essentially the phase of the sender, and then the rest of the communication is used for actually transmitting information. So we also prove that the strategy of sending a reference signal of some energy and the rest of the modes with, for example, a coherent state modulation is suboptimal with respect to the strategies I've talked about so far, even in the larger energy limit, as shown in this picture. So, quick recap. We showed essentially the advantage of explicit squeeze coherent strategies in classical communication over quantum channels. This is surprising because we are used for Gaussian channels to employ coherent states, and for a phase noise channel to employ Fock states. But we're saying basically here that in between you have this nice family, which is rather easy to produce. The squeezing values are not extreme, and it's robust to both kinds of noises. Thank you very much for your attention.
Thank you. So now's the right time for questions.
So maybe I.
Take out the mask.
So maybe I didn't get something. So you showed that if you have no losses, then with dephasing, the Fock states are not optimal for large energies, yeah? And I don't get it, because the Fock states do not feel any dephasing, yeah?
No.
For them, this is the noiseless channel. So, and we know that they can, in this instance, that they can saturate the classical capacity.
This is not lossy. So
yeah, this is not lossy, so they are optimal.
Losses. They are optimal, but...
So why you are outperforming them?
But because I'm using a discrete constellation. So I'm using states, photon states up to 2, for example, or 1, because I'm limited in the energy, okay? And also, if I try to communicate by sending a Fox state of 10, maybe this is okay. This would be optimal, but completely unrealistic. Let's say. So what I was pointing out here is that if you this is, for example, a 0-1 photon encoding, and this is an encoding with a vacuum and 2 squeeze coherent states. So of course you can beat it just because you're using more signals. But this may be advantageous in a RISC setting.
Okay, next questions.
I didn't understand the reference frame protocol. How does it work?
So it works by, so you have M modes that you can use before the phase changes. So you use one mode to send an optimal reference for phase estimation at a certain mean energy. Okay, so this state is as a superposition of a certain number of Fox states, respecting mean energy constraint. So you're saying you also have an energy budget. So if the total energy you can use here is E, you're reserving this quantity, you're reserving, I think, XE for the reference frame, okay? To produce the reference frame. And the rest of the energy and of the modes are used to actually do the communication protocol.
Okay.
Okay, next
Right.
question.
Thank you.
Yes.
Okay, maybe a very trivial one. So I understand you could go more from binary to ternary, quaternary, and so on.
Yes.
But I understand from your talk that phase information is completely irrelevant, right? So doing some constellation is irrelevant here, and this is because of the phase noise, or?
Yes, it's because of the phase noise.
So in the squeezing, actually, it's just the coefficients in the mixed states that play a role, or?
Yes, so you have to imagine that these guys, when they go through the noise, they're smeared out. They are symmetrized, if you want. And it turns out that if you start already with squeezing in this direction, orthogonal to the displacement, this is helpful. Essentially, what matters, what governs this effect is only the photon-number statistics of the state. Okay, so if you're able to exhibit a state which has good photon-number statistics, it's very peaked, like a Fox state, let's say, but it gives rise to a thermal ensemble when you average, then you're able to show an advantage. Yeah, I don't find it here, but.
Are there any further questions? If not, let us thank two speakers, to all speakers.